When you're writing an equilibrium constant K, there are a couple of rules that are helpful to remember. First of all, you never put solids or liquids in equilibrium expressions. So in the example right there, which is in the formation of sulfur dioxide, sulfur is a solid. It's reacting with oxygen, a gas, to make sulfur dioxide. Notice that sulfur is a solid. So in the equilibrium constant, we're not putting the solid in there. It's just SO2 divided by O2. Solids and liquids never appear in equilibrium expressions. This one's going to be more like a lot of the examples we're going to see where water, a liquid, is excluded. And again, remember, solids and liquids never in the equilibrium constants. So this reaction is ammonia, NH3, reacting with water. It makes ammonium, NH4+, plus hydroxide. Water is a liquid at room temperature, so it's usually not included in equilibrium constants. Products over reactants, K would be ammonium times hydroxide divided by ammonia. But again, no water, solids and liquids always excluded from K expressions. Here's a question. Which of the following is the correct form of the equilibrium constant expression for this reaction? This is the reaction potassium and water, making potassium hydroxide and hydrogen gas. Okay, so the idea is equilibrium constants are products divided by reactants. But the other thing we want to focus on here is that solids and liquids are not placed in the equilibrium constant expression. So you'll note here that potassium is a solid and water is a liquid. So neither of those will be in the equilibrium constant expression. We will put in the solutions, the AQs, the KOH on that product side, and we'll also put in the gases, the H2. So in this K expression, you'd have KOH squared on top times H2, the aqueous and the gases. But in the denominator, since everything is a solid or liquid, you would just have like 1, the number 1, like nothing is in the denominator. You don't put a 0 there because that would make your K values go crazy. Math people, and divide by 0 freaks everybody out, okay? So in this case, K and H2O, you wouldn't put them in there. You just have like an invisible 1. So if you look at all those options, answer E would be the correct one here. You'd have KOH quantity squared times H2, and in the denominator, because K and water were solids and liquids, you would just have a 1 right there. So that also brings up another thing. If everything on the reactant or the product side is solid, liquid, whatever, just put a 1 there. Only put aqueous and gaseous things in your equilibrium constant expressions. Another thing you can do with equilibrium constants is you can add equations or reactions together to give you a new expression. So let's see how this works. Here's the sulfur plus oxygen making sulfur dioxide reaction we looked at a little bit ago. Let's call this equilibrium constant K1, and it's SO2 divided by O2. Again, keeping the solids out as well as liquids if we had any. No problem. However, this reaction actually does go on to make sulfur trioxide. So if sulfur dioxide reacts with half of an oxygen, i.e. 1 oxygen atom, but oxygen's a diatomic, the have no fear of ice clear brew things. Anyway, half of an oxygen to make sulfur trioxide, we have now a second equilibrium. And in this new equilibrium, products divided by reactants, nothing is a liquid or a solid, so we don't have to worry about that. K2 would be SO3 divided by SO2 times O2 to the 1/2 power. So again, notice here the stoichiometry was 1/2, so we raise it to the 1/2 power. The square root of oxygen is the same as O2 to the 1/2 power, and we'll talk about this later. So just as a quick reminder from math, something raised to the 1/2 power is like the square root, all right? We'll come back to that in a future part. Anyway, let's say that we wanted to go directly from sulfur and oxygen to sulfur trioxide, i.e. ignore the SO2 intermediate, if you will. Well, no problem. So first of all, the K net for our overall reaction would be just sulfur trioxide divided by O2 to the 3/2 power, all right? And if you look carefully, if you took K1 and multiplied it by K2, it's going to give you this net reaction. I don't believe you, Dr. Russell. Oh, whoever said that, random student in the back of the room, I totally understand. So K1 is SO2 divided by O2. And K2, excuse me, is SO3 divided by SO2 and O2 to the 1/2 power. So we're multiplying these both together. You can see the SO2 divided by SO2 cancels out, so no SO2. And we have here an oxygen to the 1 power and an oxygen to the 1/2 power. In math, you can combine these into O2 to the 3/2 power, and the SO3 is still there. So literally, multiplying K1 times K2 will give you the K net, the one that you want, and the SO2 is kicked out. So if you have two equations and you combine them to give a net equation, overall K is going to be just the product, i.e. multiply the old K's together. I don't usually like using fractions, and if you've taken classes with me before, I will go like, oh, chemists hate fractions, but sometimes with heat of formations we have to, etc., etc. So let's say that we have an S plus 3/2 O2 making SO3, and the old K, as we saw a little bit ago, was SO3 divided by O2 to the 3/2 power. But let's say I said, oh, get rid of fractions. Chemists hate fractions. No problem. So you can multiply the whole equation by 2. All right, so if you multiply that, you get 2S. 3/2 times 2 is 3 O2s, and then 2 SO3s. The new K, though, as you can probably imagine, is going to have a different form. So notice that the new K is going to be SO3 squared divided by O2 to the 3rd power. Well, if you take the old K, this thing up here, and you square the whole thing, notice how this is the same idea. It's like the old K squared. So we multiplied everything through by 2 to get the new K expression. And if you had an old value for K, you can turn it into the new value by squaring it. So let's say that K old was a value of 10, and we wanted to figure out the value of K new. Well, no problem. We would take the old K, 10, and square it. 10 squared, the new K would be 100. All right? So you can literally transform a K value into a new K value if you multiply the stoichiometries together. So if I said multiply everything by 2 to get rid of that fraction, you could absolutely translate your old K into a new K. So this is kind of a trick of the trade, which can be really helpful. Finally, you can also change direction of an equilibrium constant. So instead of thinking about sulfur plus oxygen going to sulfur dioxide with K equals SO2 divided by O2, again, remember to keep the solids and liquids out, let's say we wanted to reverse it, and we wanted to think about it from sulfur dioxide's perspective, breaking down to sulfur and oxygen. Okay, no problem at all. The new K would be the oxygen gas on top divided by SO2 on the bottom. Again, no solids and liquids. And if you look at the old K versus the new K is just 1 over the old K. If you went 1 over SO2 divided by O2, it would become O2 divided by SO2. So the new K is just 1 over the old K. All of these transformations can be found in greater detail in a handout I have called Manipulating Equilibrium Constant Expressions. It's in the companion, and it's also online. If you can't find it, let me know, and there's examples of how this works. But the real important message of this section is that if you are working on a lab, all right, and you're thinking about it as sulfur dioxide breaking down to sulfur and oxygen, you're going to have some value of K. And maybe in my lab, I'm thinking about it as sulfur reacting with O2 to make sulfur dioxide. Well, our K values should be different from each other, all right? We can translate one lab's work into the other by going 1 over the K to get the other lab's K, but by default, the numbers could look very, very different. And this is something in chemistry you have to be very aware of. Everybody has to use the same form of the equation for the answers to make sense. You can And sometimes it'll be better to think about it as SO2 breaking down or forming SO2 from the reactants, either way. But you can translate one into the other as long as you're hip to how these transformations happen. So it's a good kind of section to pay attention to. Here's a reaction. The compound N-butane is breaking down to isobutane, and it's in equilibrium. Isobutane is also known as 2-methylpropane, or just methylpropane if you want. But anyway, the K value here, 2.5. Well, let's say you wanted to know the value of the reverse reaction. So notice how isobutane was the product. Now isobutane is the reactant, and the N-butane is shifted as well. So to go from an old K to a new K, where it's the reverse like we've done right here, you just want to go 1 over the old value. So to figure out the K value here, you'd go 1 over 2.5 in your calculator. That number comes out to be 0.40. So that's how you would calculate the new value of K. It's 1 over the old one in this case. Remember, the K values will never be negative and they won't be 0. So answer C is just kind of silly, but this is how you can translate one K into another. All of our equilibrium constants so far have been technically a K sub C, and a K sub C is the most common kind of equilibrium constant. It's an equilibrium constant based on molarity, or moles per liter. But there are other kinds of Ks, and we're going to look at some of them in this whole class. But one that's definitely worth talking about is what's called a Kp. If you have an equilibrium constant that's a Kp, it's an equilibrium constant based on gases. P stands for pressure. And if you remember from Chem 222, atmospheres are the dominant pressure term used in chemistry. So a Kp, instead of using moles per liter, which is what we've been using so far, we would use atmospheres of gases. So Kp is only applicable towards gases. You really can't have a solution pressure per se, although you can argue osmosis, but that's a different story. But anyway, almost all the time Kp is atmospheres-based pressure equilibrium. Kc is moles per liter, and you can have gases, so many moles and so many liters of volume, all right? That's totally fine. Gases can be Kcs or Kps. Solutions, though, aqueous things, pretty much just Kc. Now, when it comes to atmospheres, it's really important to remember that 760 millimeters of mercury equals an atmosphere. So if you're given a pressure in millimeters of mercury, make sure you translate into atmospheres before you do any Kps. Here's an example of 2 different ways you could write this reaction. This is nitrogen and 3 hydrogens making 2 ammonias, and this will be something we'll talk about more. If you're going to write it as a Kc, that's a moles per liter based equilibrium, you would write it as square brackets, which means moles per liter of ammonia squared on the top divided by nitrogen times hydrogen to the 3rd power. We're raising everything to the stoichiometries. But in this case, you could also have a Kp. Everything there is a gas. So you could have the pressure of NH3 squared divided by the pressure of N2 times the pressure of hydrogen gas to the 3rd power. Either way is fine. And remember, Kps, you have to use atmospheres. Kcs will all be moles per liter. You can translate a Kp into a Kc if it's the same reaction, and this is the conversion you would use. Kp equals Kc times RT raised to the delta N. So let's talk about how we would do this if we had to convert Kc into Kp, or Kp into Kc for that matter. First of all, T is the Kelvin temperature. Anytime you've got gases, you've got to use Kelvin temperatures. So that would be that 273.15 plus the Celsius temperature would give you the Kelvin temperature. R is the gas R, the 0.082057 number. And the units for that are liters atmospheres per mole Kelvin. You would not want to use the other R, the energy R, which we will use in other parts of the lectures. Delta N is the change in moles of the gas. Remember, delta always means final minus initial. So that would be the final moles of gas minus the initial moles of gas. So as an example, if we're looking at that same reaction where nitrogen and 3 hydrogens combine to make 2 ammonias, delta N would be the final moles of gas, 2, minus the initial, and there's an invisible 1 by the N2, so 3 plus 1 would be 4. So you can see that delta N in this case is -2. Delta N's can be positive numbers, they can be negative numbers. Once in a while there's 0 if you don't have any change in moles of gas. There's all different kinds of possibilities here. So this is actually now a new type of equilibrium constant. We looked at Kc, moles per liter based equilibrium, which is by far the common one we're going to use, but this is a Kp, an atmospheres based equilibrium constant. This is another handout that I recommend you have access to. It lists different types of equilibrium constants that we might see in Chem 223. We're going to see several different kinds of equilibrium constants as we go through the next chapters. And if you forget later on what a Kp is, which is totally fine, go back to this list. It'll tell you what it is and you can go from there.